As Jerry said, good afternoon, everybody. My name is Nigel Forrester. I represent Concurrent Technologies. As you can probably tell from my accent, I am an alien from the UK. And our focus is predominantly Intel-based processing engines and boards, and hence the topic of my discussion this afternoon. For those of you who are able to stay awake after that nice lunch, is constructing VPX-based rugged microservers. So there's a couple of interesting points, some of which are not too surprising that we're going to cover, and a couple of quite surprising things which some of the other speakers have sort of touched on, and I'm going to just delve into in a little bit more detail. The topics I'm going to cover are really to do with the Intel CPU performance and processing trends, and also the Intel GPU capabilities. One of the other areas that we see some dramatic changes over the last couple of years, and more to come really, is in storage. And then what I want to try and do is sort of tie together what those mean with reference to 3U VPX, predominantly 3U VPX microservers, which is what I'm talking about today. And then if we have time, we can take some questions. So, bit of an eye chart. Some of you might be able to just about see the graphic. But this is the not so surprising bit. So really in the top left-hand corner, I'm showing the sort of what I term metronomic die shrink microarchitecture updates that we get as a virtue of using Intel-based silicon on our boards. And for the last 6 generations or so on what's termed the Intel Core product line, sometimes the dates have been a little bit off. Intel were perhaps a little bit later than they'd have expected introducing their 5th generation Broadwell architecture products, and then perhaps a little bit earlier in announcing their 6th generation Skylake products. But the reality is that we keep getting this ever increasing improvements in terms of things like cache capability, the memory technology that they're using, little improvements in terms of CPU processor speed, some of the technologies that they're using, some new instructions that they've introduced, and all those actually add up. So most of our customers, and I'm sure this is true for all the other people in the room, especially for the types of programs that are running with 3U VPX, they don't tend to get upgraded very often. The refresh cycle is quite long. So even if we don't see huge improvements per generation, that actually adds up to quite a significant amount. And so the little snapshot I've got on the bottom right, which is not true representation, but it's a couple of data points, compares figures which we've got from 4th generation and 6th generation devices, where they're 15–16% sort of difference in that particular metric that I'm showing there. And that's, if you actually, from an application point of view, that can be very valuable if you're looking at that over a few generations. What is perhaps more interesting and is more of a dramatic increase is that from their 2nd generation core products, Intel publicly stated that they were going to increase their integrated graphics. Now, you could look at this the other way around and say, well, actually, if you roll the clock back 5 or 6 years ago, Intel integrated graphics was synonymous with terrible. It was barely usable, even in 2D, but they've delivered some massive performance increases. Sometimes, as you can see from the sort of snapshot I've got on the bottom of the table there, which compares single precision floating point operations per second, there's a multiple increase per generation. And that's a result of either more execution units, faster clock speeds, better architecture in the way they develop their graphical processor units. Effectively, there's a couple of takeaways really that I want to deliver from this slide. First of all, I think it's fair to say that many of our customers today still are not using those GPU resources that Intel are delivering as effectively as they could do. Quite a few people are investigating that. Many of our customers traditionally have used a separate GPU from a CPU. But there are some advantages with the Intel integrated architecture here. First of all, it's supported by OpenCL, and that spans, as one of the speakers before the lunch break was saying, spans across different architectures. So it gives you a degree of independence in what you're doing. It's quite well supported. It works pretty well from what I've heard. The sort of other advantage really of OpenCL is that you can provision it so that you can actually say whether your application will run on both the CPU and the GPU. So effectively, you can treat your resources as a single bucket if you want, and actually have everything running on that bucket, or you can deliberately segment the CPU and the GPUs and run whatever's more appropriate on those devices. One more quick thing, just in case you're wondering why there's two things at the very right-hand side of this table that might sort of confuse you. So first of all, the naming convention that Intel's been using has been very consistent across their generations of products, starting with the first generation Core. These are Core embedded versions of Core mobile chipsets. We had first generation, second generation, third generation, fourth generation, fifth generation. And the top of the range product, which supported ECC memory, was always called an i7 device. Starting with this sixth generation Skylake architecture, they've actually rebranded the top-end ECC memory-compatible variant as the very snappily titled Intel Xeon E3 1500 processor family, which is a little bit of a mouthful. It's also quite confusing for customers who think, well, I want the progression from the fifth generation or fourth generation or third generation i7, and now we're actually calling that, effectively that device, a Xeon device. I'm sure there's a good reason why Intel are doing that. And the other point you might be wondering about, when Nigel's been saying that there's been dramatic increases in GPU performance, the figure for the sixth generation 2015 Skylake architecture device on the right-hand side is actually less than the fifth generation. So currently, within this processor family, the highest embedded capability GPU device with an integrated GPU is actually a fifth generation Broadwell-based part. And that's mainly because Intel initially delivered some early Skylake parts. And the expectation is that at some point in the future, they will deliver a significantly higher performance Skylake-based part. The other thing which, again, had a very nice segue from Ken of Elmer early this morning, was to talk about one of the other disruptive technologies in this space, where within the same power envelope that we've been using, whereas Intel have been consistently upping the amount of GPU resources at the expense really of sticking with a quad-core CPU, they've introduced in 2015 this Intel Xeon D1500 processor line, which they've introduced as an 8-core, 16-thread device, and have publicly stated that in Q1 2016, they will be introducing some higher core count devices, so both 12 and 16 core devices. So this is extremely good for those customers that can take advantage of multi-threaded CPU applications. It gives them another option, effectively. It's like a server-grade product. There are some very nice features to do with this product, one of which is that it has integrated 10 gig Ethernet in the device. It also has some server-grade type caching capability. It has cache management technology and cache measurement type technology, so you can actually tweak your application to use the cache very nicely. So there's also, it works like Xeon architecture products in terms of the way that the turbo technology works. So if you go back to the Core i7 mobile type product line, they advertise both a base frequency and a max frequency. You achieve the max frequency by turning the turbo on. On a mobile generation product, the turbo actually kicks in for quite long periods of time. It's about 30 seconds, I believe. And there's a big difference between the base and the max frequency. So you can actually, some customers struggle with the idea of turbo because it can be quite non-deterministic. And that's in some cases, not desired. In the Xeon product line, the turbo, the difference between the base and the turbo frequency is much smaller, and the turbo only kicks in for very short periods of time. I think it's about a second. So it gives you a much more deterministic type of performance, but it is still a usable upgrade. The figure at the bottom of the slide here is comparing a 4th generation Core i7 based product, a specific, well, actually this is a pass mark rating, with a rating we have off our latest Xeon D1500 8-core product. So not surprisingly, it's, if you're just comparing CPU with CPU, and you've got an 8-core CPU running at a pretty high frequency rate, you'd expect to see a sizable difference, and that's what we do. If we were taking other, if you had an application that wanted to use the GPU resources, then it's not really a fair comparison. But nevertheless, it's a good idea that if your application can make use of those CPU multi-threaded resources, it's a very valuable type of technology. So I also wanted to talk a little bit about storage technology and advances. Not something I've heard so much about this morning, but this also seems to be quite a disruptive technology, especially in the embedded space. Almost all of our customers want long life, rugged, high reliability, high capacity type devices. And we've seen some major changes, perhaps sort of less so from the interface point of view, where we've seen incremental step changes in speed from the original SATA through to SATA 600, and now we're starting to see PCIe-based interface being used for storage medium moving forward. But the real change has been in the use of solid-state storage devices, which have gone from being, maybe five years ago, relatively rare, small capacity, not enough perhaps for many applications, to being mainstream-based devices. So in a 2.5-inch form factor today, you can get up to 2 terabytes of storage in that medium. They are now quite well tried and tested. The actual storage controllers are well used and tested. And in the sort of what I sort of termed on the right-hand side of the slide, more the embedded format, we do, as I'm sure many other vendors do, small modules that fit onto our processor boards. This particular one is about the size of a postage stamp, a little bit larger. So the chip on that device is 16 by 20 millimeters size. We're shipping 64 gigabyte capacities up to 128 gigabytes this year. That's actually enough for many applications if you're not doing mass storage. It's also very easy to do things like conformal coating. So it's easier to make those devices in a heavily rugged environment. So there's been major changes that have meant that many more applications can make use of those storage facilities. So I've got a couple of quick sort of summary really slides to sort of show the sort of things that can mean and why you can do more really within the same sort of size envelope. And I've tried to take some fairly abstract examples. These are you can do lots of other things with these types of products, but one of the areas we've seen a lot of interest is things like image processing. So actually using the GPU resources on some of the processor boards to actually do some meaningful DSP type or FFT type calculations. We've also seen a lot more usage of local PCI bus connectivity between mating boards. So whether they're boards from ourselves or boards from other vendors, the ability to construct small systems without having to have a switch gives a very nice, compact, lower cost, simple to manage solution if you can make use of those PCIe connections in a simple way from your application. So just before the break, one of the other presenters was talking about their middleware layer, which does a very similar sort of thing. We have a product called Finesse, which effectively abstracts your application. So if you have a standard socket-based application that will run on a load of servers connected with Ethernet links, that will run in exactly the same way across PCI-based devices, even irrespective of how they're architected. So we have a lot of independence there, which is a very nice and easy way to construct those sort of solutions. We've also seen quite a number of customers wanting to use heavyweight CPU type applications. So So again, there's a couple of examples here. The one at the top shows a number of the Xeon D boards, again, connected together via local PCIe links, but also we've seen a number of perhaps a more traditional type of application at the bottom there, where boards are connected via 10 gig Ethernet or something like that on the data plane with a switch, so it allows a much higher level of scalability, slightly bigger capacity type of systems. And I've also seen, and obviously I've shown individual blocks here, but we tend to see in reality customers using a mix. But for example, you can get now very small form factor systems with RAID capabilities, perhaps 8 gigabytes capacity, all mated off a single processing resource within a chassis, perhaps with some other processing there. So in conclusion, what I've really tried to show is that from an Intel embedded perspective, things are moving along very nicely. Within that same vital swap envelope, there's a lot more ways you can slice up your data. You can probably architect a system this year much more in smaller number of slots or a more economical way than you could maybe even just 1 or 2 years ago. There are more capabilities yet to be used, particularly on the GPU side. As I said, a lot of the capabilities are good enough for some of the applications that we're seeing within 3U, and that's really driving a lot more activity, I think, within the 3U space, which is good enough for many of those applications. And just to sort of summarize, there are more to come this year, so watch this space.